Today I will start with a general introduction to solar energy conversion. So this is the contents of my new book that has been just published. This is the Physics of Solar Energy Conversion by CRC Press. And in the book, we have described the principles of several fields related to clean energy production and advanced materials like photovoltaics, the solar fuel production, also energy storage in batteries and also lighting. So this is a book about energy materials and interfaces for making devices and understanding the principles. So I want to explain how this book began. So basically, since 1950s, we had the solar energy conversion by silicon photovoltaics, and the dominant way to understand this has been physics-oriented, because you have the production of carriers, and then you have like drift diffusion equations. So the production of photovoltaic action was very much based on the semiconductor transport equations, because this is just a homogeneous piece of materials with electrons and holes move. So this is the natural way to understand it. But in the final years of the 20th century, there appear different concepts for making photovoltaic devices, like sensitized cells is based on a nanostructure that can transport the carriers in a liquid medium, and you have dyes to capture the light. So there is a process of injection to this semiconductor, and then you decouple a single material into a mixture of materials. So this is in principle quite different from the homogeneous semiconductor. And based on this concept, you can make solar cells with organic materials, and in particular, you can make like these multicolored solar cells. So this is the dye-sensitized solar cell, mainly the work of Michael Gratzel and then many others, and it was well developed until 2010. So this is the first concept. And another concept is the fully organic solar cell. So in this case, this is a blend of organic materials that are electron and hole conductors. So here you have also excitation and charge separation, and you have a transport in an heterogeneous nanostructured material. Another interesting concept is the quantum dot sensitized solar cell. So this is similar to the dye sensitized solar cell, but uses an inorganic semiconductor, usually a quantum dot, for the absorption and injection of carriers. So then these things were developing, and some have continued, others not. So now the organic solar cell now is very high efficiency and robust, but in 2010 appeared a derivation of the sensitized quantum dot sensitized solar cell, appeared by the work of Professor Tomomi Asaka in Japan, and it was covering the nanostructure with metal halide perovskites. So this perovskite is a combination of several materials, and then you can make also thin film solar cells by solution process method. So in principle, this is quite cheap, and then there was an evolution from the nanostructure semiconductor to a full thin film of perovskite, because the use of the nanostructure here was more like a kind of contact. So already in 2013, there was a very high efficiency of 15% after just a few years of discovery. And then this started going up. So this is the general table of efficiencies of photovoltaics, and this started going up. and it has reached now 25% efficiency, which is very high for a solution process solar cell. So here it is more detailed, and you can compare the fast rise of efficiencies of perovskite, which is now around here, compared to the historical evolution of other photovoltaic technologies. And this was also by increasing technical and fundamental knowledge about the preparation of the perovskite. So, in summary, over the last 30 years, there has been a lot of novelty in photovoltaic materials, and this combination of methods, techniques, different materials, interface, and structure requires a new understanding of the photovoltaic materials. And this is the basic concept in which you have an excitation of a semiconductor, and then it's going into other or the same materials, but then we need some principles that describe the diode solar cell and a thick semiconductor like the perovskite solar cell or the silicon solar cell with the same concepts. So this was developed over many years, and the main concept is that when you have a semiconductor, you have carriers in two different states, and they are basically in equilibrium with the surrounding radiation. And then when you produce light, you have an increase of pumping to the high energy state, and then an increase of recombination, which is falling down from the high energy state to the holes here. So you create carriers by photoscitation, you lose them by recombination. With this process, you create more carriers in the upper state, and you create a separation of the chemical potential. And this is an internal photovoltage, but not an electrical voltage that you can measure. To obtain a voltage, you have to supplement the solar cell with additional parts, which are the selective contacts. So the selective contact is one material that will take one type of carrier only, so that here you get an equilibration to the chemical potential or Fermi level of electrons, and at the other side you get equilibration to the Fermi level or chemical potential of the other carrier, the holes that are at the lower state. So that now you can really obtain a voltage from the solar cell, and you have a complete solar cell. This concept has also been very clear in silicon and other type of solar cells. For example, in the book of Peter Borfeld, he describes the same concept. But it was then generalized to all the new types like the time sensitized, quantum dot, perovskite. And so the image that we have is that you have a semiconductor with selective contacts and have like three steps. One is light absorption, pumping up. Then you create an electron hole pair, and this must be separated, otherwise it goes germinate recombination. And finally, you need extraction, and when you have extraction, you create current, electrical current, you create photocurrent. So another way to see it is to have regeneration, competing recombination, and extraction. So you have these three main processes to count in the balance of carriers. And of course, you are interested in carriers going out, because the carriers recombined inside don't give you any electrical work. So this is a loss, and this is the main process to control, is to diminish the loss and send out as many carriers, and of course absorb also as much light as possible. So from the picture of the selective contacts, you can see the process of creation of photovoltaics, because the internal state of the semiconductor is taken by the contacts, and then you can have photovoltaics. This is a very simple model with several assumptions, which is nice for getting an idea of how the solar cell works. But of course, you see the Fermi levels are straight. The extraction is very fast. You have Some assumptions, this of course can be improved by using transport equations to make a more realistic model if the solar cell is very thick, which is when you will have gradients, etc. But for starting, this model is very nice because now you have to consider also a balance of lights, because you're having the illumination pumping carriers upwards, and you're having the recombination. And when the recombination is radiative, it will produce emitted light. So this is an important concept in which not only you see the electrical flow, but also the flow of photons coming in and going out in order to control the operation of the solar cell. The other point is that in the solar cell, you can control the voltage externally. You can modify it. So when you control the voltage, you can control the internal recombination. So you can control how much current is going out or coming in. And from this, you can make a balance of all the currents going on in the solar cell. So because you are in the dark, you have the external current, the recombination current, and the initial generation current. And when you put light, you have more photogeneration. So you write a balance of these currents, and from this you obtain the fundamental diode equation, which is just a balance equation of a solar cell with selected contacts. So you don't need any transport equation to write a diode equation. And this is a nice explanation of the origin of the solar cell as a diode that is illuminating. So when you modify the internal voltage, you can move and change the external current and obtain JV curve very easily from this simple model. We can go further and consider the balance of illuminations, and you can do here some fundamental considerations about the equilibrium of the radiation coming in and going out. So for example, you can get a fundamental recombination constant for reactive recombination, and from these concepts, you can make a general analysis of the possible efficiency of a solar cell, and this is called the QUEISSER efficiency limit. So then in this method, you describe the solar cell, as I just said, a semiconductor with selective contacts. It interacts with light, and the absorber is a material with a sharp bandgap. And then you assume that there is the tight balance of light coming in and going out with only radiative emission. Just by using these ingredients, you can obtain a fundamental limitation to the efficiency by taking into account the different losses of the physical effects of this model of the solar cell. You can obtain the possible power in function of the bandgap of the material, which is maximum around here, 1.5 electron volts. In summary, there has been a lot of changes, generalization, and interest in the photovoltaic materials over the last 30 years. So then I decided to summarize the situation in a series of books. The first one was about equilibrium concepts and kinetics for nanostructured energy devices. The second about carrier transport, and the third about the photovoltaic principles. And then, after the collection was complete, this has been now combined into a single volume, which is the physics of solar energy conversion. And this now makes this broad view for a range of materials about the principles and applications of solar energy conversion, and it covers the discovery of perovskite solar cells, also the organic solar cells, and also energy storage and hydrogen production for water splitting. So now the book is published and available if you are interested in understanding this type of scientific field.